Merci. Well, good morning. I'm Gabriel Catren. I'm one of the organizers, together with Mathieu and Anel, in the scientific organization, and Julian, Federico, and Christine. So it's a big pleasure to welcome all of you to this event. First of all, I would like to thank the different persons and institutions that made this possible. So, first of all, the Institut Poincaré for hosting this event. Secondly, I want to thank the administrative staff of the institute in which we work in the University Paris 7, who help us with the organization. Afterwards, I want to thank also the European Research Council for the financial support. And also I want to thank all the speakers who accepted to participate, and all the participants who are here. It's really an honor to open a conference with this with such an incredible list of participants. So let me also say that we understand this conference as a sort of first step towards the edition of a collective book. The idea is to include part of the discussions after each talk in the book. So this is why we are only having just a few talks per day and a lot of time for discussions. So please feel free to use this time. And I also want to say that this conference has a sort of dual nature. On the one hand, it's a conference organized in the framework of a research project, of a research team in philosophy of mathematics and physics. And on the other hand, it's an event in which we have only invited scientists, and it takes place in a scientific institution. So regarding this point, I want to say that, strictly speaking, we do not understand this conference as a conference in philosophy of science, but rather as what we could characterize as philosophy in science. This means that we do not understand the philosophical reflection as a sort of external approach that would take science as an object placed in front of the philosophical reflection, but rather as an internal dimension of science itself. This means, of course, that science is not only about proving theorems, constructing theories, and making experiments. Science is also about concepts, ideas, programmatic decision, historical perspective, research programs, principles, and so on. And we think that it's very important to recognize the importance and the scope of this conceptual dimension of science, and we think that it is the task of scientists themselves to perform this task. Of course, this does not mean that we are going to avoid the technical parts of mathematics. It simply means that we want to put these technical discussions at the service of this kind of wider philosophical reflection. So that's all for the moment. I wish all of us a great conference. And now we'll start with a talk by Kock on synthetic differential geometry. Yeah, please.
I think this is working, right? Well, first I want to thank the organizers for inviting me to speak at this prestigious place. And secondly, the title of the talk is New Methods for Old Spaces.
It's not being displayed. I don't know why. Let's start.
New methods for old spaces. This is slightly polemic because the title of the conference is about new spaces. And also, I should say that the method I'm going to talk about, the synthetic method, that's not really new either. That's at least a couple of millennia old. Synthetic geometry, as we know it today, was at least existent at the time of Euclid. And what does synthetic mean? Well, this means that you are considering the objects and their mutual relationships, but without consideration of what the objects are made of. So such a theory is typically axiomatic because you don't care what, for instance, the notion of line means. But the synthetic method received a new impetus with the advent of category theory, because then it became possible to state in a more clear way what relationship means, or you get a more comprehensive notion, namely the notion of map in a category. So today I would say a synthetic theory would essentially start, in particular, a synthetic theory of spaces would start with giving as basis a category of spaces. We don't define what a space is, it's just an object of this category. Typically, synthetic differential geometry would start with saying the category is a topos, but it's just a canvas on which you paint. It doesn't matter. It should just have sufficiently good properties. But usually one also starts saying, consider a topos with a ring object in it, which you think of as the number line. That's also some of the primitive data. So typically the actions that we are using in synthetic differential geometries start with saying, given a topos and a ring object in it, a commutative ring object in it, and then give actions for this data. And this is a theory that has been around for 50 years more or less, or even older. In some sense it goes back to Kähler and Grothendieck. But the thesis I want to advance here is that for differential geometry, the notion of number line is really not the central concept, but rather the neighbor relation. Many concepts in differential geometry can be formulated entirely in terms of the neighbor relation without any consideration of a number line. So what is you often see that argument or discussion in classical text for neighboring lines, or consider the limit of neighboring line, the intersection of neighboring lines, and so on. So the presentation I want to give makes this notion of neighbor the central one. So the neighbor relation, or better, the first order neighbor relation that you have in differential geometry is symmetric and reflexive. It's not transitive as this would make some of the theory collapse. Also, the maps between spaces should preserve this neighbor relation that the spaces are assumed to have. Well, why it's not transitive? Because even in daily speak, your neighbor's neighbor need not be your neighbor. So, for the neighbor relation, I use this tilde symbol. When I say it goes back to the time of Kähler and Grothendieck, is because in and the circle around Grothendieck in algebraic geometry in France in the 50s, they considered what they call the first neighborhood of the diagonal of a scheme. But as I say, I'm not here considering what the objects really are. I'm making an axiomatic theory, or presenting an axiomatic theory. So the set of pairs of neighbor points is what they call, or would call, the first neighborhood of the diagonal. Well, one aspect of having a topos as the background on which you speak, or the canvas on which you paint, is that a topos is almost like the category of sets, which means that you can talk about the objects as if they were sets, and reason with them as if they were sets, just making sure that you don't use non-constructive principles like excluded middle and so on. So therefore I can also, for a given element of a space, say X, talk about the set or the space of neighbor points of X, which, borrowing a term from non-standard analysis, one could call the first order monad around X. You have also higher order monads, which I shall not say much about in this talk. Well, sorry. One of the basic notions of differential geometry that you can express in terms of the neighbor relation is when two spaces are tangent to each other. Well, I should say two subspaces of a given space are tangent to each other at a given point X common to both of the spaces. Namely, that insofar as the monad around X is concerned in the ambient space, these spaces S and T have the same intersection with that monad. Here's a very rough picture. You can see I'm trying to draw the monad here, and insofar as this monad is concerned, there's no difference between S and T. They have the same intersection with the monad around X. Here's another more civilized picture of the same. When I say more civilized, it's because one of the spaces here happens to be a line. But I want to stress that at this primitive stage, there's not even a notion of line yet. We are in a pre-civilized age. Now I want to just present some classical differential geometric notions that can be expressed in terms of the neighbor relation and nothing else. For instance, the notion of geometric distribution on a space M. This is a symmetric reflexive refinement of the neighbor relation. So not only do you have a notion of when two points are neighbors, but also when they are neighbors in a strong sense. So if I draw the neighbor relation with a single line, the strong neighbor relation is drawn with a double line. That's the notion of when a distribution is involutive. This is simply to say that if you have a configuration like this, X and Z are strong neighbors and X and Y are strong neighbors, and Z and Y are neighbors, then you can conclude that Z and Y are neighbors. Well, I should better show some pictures. Here's a picture of a non-involutive distribution on R3, three-dimensional space. 2 points are strong neighbors if they, well, it's not an exact picture, of course, but if they lie on some common little of these flat pieces. Here's a picture of an involutive one. In fact, in 2 dimensions, all distributions are involutive. And now one of the important theorems in differential geometry can be expressed in terms of this notion that any involutive distribution admit a maximal connected integral subset. For instance, when you have this involutive distribution in the plane, which I've drawn a very poor picture of here, the integral subsets will be the curves that run along the lines. An old method you learn in calculus books for solving a first order ordinary differential equation by this diagrammatic method. This is really an application of the Frobenius theorem. I should say that synthetic differential geometry does not provide means of proving such an integration result, because basic integration results in differential geometry very often depend on the completeness of the real number system. And such a thing we don't have, and we don't really have the notion of limit on this basis. Let me describe another geometric a notion that can be expressed in terms of a neighbor relation, namely an affine connection on a space. This you can express by saying, given a configuration like this, 3 points, 2 of which are neighbors to the third, so Z is a neighbor of X and Y is a neighbor of X, then you can complete it by a fourth point, neighbor, call it lambda X, Y, Z, which is neighbor to Z and neighbor to Y. You want, of course, you want to think of lambda X, Y, Z as the result of transporting Z along the segment from X to Y, a parallel transport. So therefore it's natural to say that if Z equals X, then the result of transporting X just gives Y. And also if X and Y are equal, then you do not transport at all, and then the result will be Z. You can prove on the basis of the axiomatics that I will present later in the talk in chapter 3, I think, that this does agree with the notion of affine connection that you have in classical differential geometry. Here it's just presented in a purely synthetic and quite geometric way, because affine connections is, after all, a notion of parallel transport. So the data is that you have parallel transport infinitesimally. Well, I haven't used the word infinitesimal yet. In fact, it doesn't belong at this stage, because infinitesimal is, so to speak, the quantitative aspect of the notion of neighbor. Neighbor is a geometric notion, whereas infinitesimal, that is something you can apply for numbers. And we haven't yet looked at a number line. Well, the arrow that we had here in the definition, or the description of affine connection, is just to indicate which aspect of is the active. You move from X to Y, and Z is the thing that you move. But many connections happen to be torsion-free or symmetric. This means that there's no difference. Lambda X, Y, Z is the same as lambda Z. Oh, sorry. You can interchange Y and Z. Gives the same result. So there's no need to carry along this little arrowhead I had before. You can also express the notion of geodesic for an affine connection. It's simply a subset which is stable under the operation, the partially defined operation lambda. We can also express the notion of curvature for an affine connection in these terms. Namely, consider an infinitesimal triangle. This means 3 points which are mutual neighbors. This was not the data we had for an affine connection because there the corners, so to speak, the y and z, they were not assumed to be neighbors. But if they are neighbors, then we have what one might call an infinitesimal two-simplex or an infinitesimal triangle. And if you have such, you can ask, starting with a point z that is neighbor to x, then you transport it around the triangle and come back. And then you have a new neighbor of x0. This means that such triangle gives rise to an automorphism of the monad around x0, namely the result of transporting around the triangle. And you may so this is the curvature of the connection. And if the curvature gives, if every z neighbor of x0 gets back to where it started, in other words, if the curvature is the identity map, then you call it a flat connection. The curvature is actually an example of a combinatorial two-form. Here it's a two-form with coefficients, with local coefficients, because the value of the curvature gives an automorphism of the monad around x0 for each x0. So you have really a bundle of groups, namely the automorphism groups of the various monads. Well, when I say automorphism group of a monad, I of course understand that the center of the monad remains fixed. Well, let me for simplicity talk about differential forms with values in a group instead of in a bundle of groups. Then I can also talk about the differential K forms. This is just laws which to an infinitesimal K simplex, which means a K plus 1 to on mutual neighbor points, assigns an element in the group with the proviso that if two of the elements are equal, two of the vertices, I should say, in the simplex are equal, then you get the identity map. I should say that this a synthetic treatment of this notion of differential group value form I learned from Bocuse and Joyal many years ago, and it has been developed partly by myself and partly by Breen and Messing, who have a paper on combinatorial differential forms. So this is also a thing that depends on, or that lives at this very primitive stage where you have no other notion than the neighbor relation, no other structure than the neighbor relation. I should say that for many groups, it's not automatic, but for many groups, you will have that it's, well, let me talk about one forms, that they are alternating in the sense that if you interchange x and y, or x0 and x1, I should say, then you get the inverse element in the group. Note that I could similarly talk about alternating k forms. This means that when you interchange any of the k plus 1 elements, you get the inverse element. So note that for combinatorial differential forms, they have an alternating property. A k form has an alternating property with respect to the symmetric group in k plus 1 letters. Well, if G happens to be the additive group of a ring, then you have a further structure, namely the wedged product. Given two forms omega and alpha, two one-forms omega and alpha, you can define a two-form which to an infinitesimal two-simplex x, y, z associates the product omega xy times omega. Oh, that was, sorry. I went down to it. Omega wedge alpha on an infinitesimal two simplex is omega applied to the first two times alpha applied to the last two. And here you use the times, which is not the one form was with values in the additive group of the ring. So even here's the multiplication of the ring. Let me go back to the multiplicative group value differential form, where it's a group structured multiplication that counts. Then you can define the co-boundary of a one form omega. It takes two simplex into omega xy times omega yz times omega zx. It looks like the co-boundary for in ordinary simplicial algebraic topology, doesn't it? But it's correct. There's an isomorphism between the algebra given a commutative ring R plus times. There's actually an isomorphism of differential graded algebra, algebras between the combinatorial forms described or sketched here and the classical differential forms and their co-boundary exterior derivative and their wedged product. This can be proved. Many of the things I say, I of course don't have time to give proofs. They can be found in a book and some articles which I will give reference to. Now let me mention another differential geometric notion that lives on this primitive stage, which is the notion of an envelope of a family of, let me for simplicity talk about curves in the plane. So the space is some plane, or actually I don't have the notion of plane and line yet, so it could just be a parameterized family of subspaces of a given space. But let me, for illustration, take a family of lines in the plane. Here you have a picture which goes back to, I think, Huygens in the 17th century. You consider a curve T, and then you have the family of normals to the curve T. So all these angles are right angles. And you have the evolute of these lines, well, it's called the evolute of T actually, which is, the picture is like that. When I say parameterized family, this means that the parameter space, which is here's T, also is equipped with a neighbor relation. Any space is in the presentation so far. How is the envelope, in this case the evolute, defined? Well, it's defined in terms of the characteristic points, in this case, where the characteristic point corresponding to the parameter value T0 is, well, in differential geometry text you would say it's the limit point of the intersection of ST0 with its neighbor lines. Take a neighbor line to the line at T0, say ST, and then you let T move to T0, and then the intersection line, the intersection point which these two lines have will approach a definite limit position. This is how the evolute, or more generally the characteristic point, that's how the characteristic point is defined, and the envelope is then the union of the characteristic points. Well, this works rather fine for curves in two space, because two curves in non-singular situations have a point as the intersection, and there's no doubt about what a point is. But suppose you have a one-parameter family of surfaces in free space. In non-singular cases, an intersection of two surfaces in free space is a curve in free space. So if you do the same, or use the same idea in free space, you would say take the limit intersection curves of the surface ST as T approaches T0. I want to quote from a classical text on these issues by Courant. This curve, i.e. the characteristic curve of this family of surfaces, is often referred to in a non-rigorous but intuitive way as the intersection of neighboring surfaces of the family. So there is some reservation in Courant's way of speaking here. It's non-rigorous, but it's intuitive. Why shouldn't we have rigor and intuition go together? Well, Courant later on in a coordinatized situation says, if we let h tend to 0, h is the difference in the parameter, if we let h tend to 0, the curve of intersection will approach a definite limiting position. I think this is not rigorous either, because what is a limiting position of curves in free space, in particular since we're talking about non-parametrized curves? Then you would have to have a topology on the set of subsets of the plane, which I don't know, but it's in the same few lines later on. Courant gives this. I shall. Oh, wait a moment. I shall return to that will be later in the talk, I hope, how the synthetic way of speaking about these things will give a very concise and rigorous description of characteristic curves, or more generally characteristic set of a parametrized family of subsets of a space. Well, now I've shown you some things that can be done on this very primitive level where you have nothing but a neighbor relation. Of course, we don't want to remain in Stone Ages where you don't. I don't imagine that in Stone Ages you had a notion of line that came with the civilizations, I think. So now we move into the age of civilization, where you have a notion of line, and hence you have, after some time at least, Euclidean geometry. So now I have to discuss how the neighbor relation interacts with the Euclidean geometry. Well, here's one principle where it is not compatible with Euclidean geometry as it's discussed in Euclid, namely, I call it a principle. I don't want to have it as an axiom. I'll present the better axiom later, but then we can prove the principle. Namely, given two lines in the plane, I call them affine subspaces because I want to say it more generally. Given two lines, L1 and L2 in the plane, and a point common to both, then if they have the same intersection with the monad around that point, they are equal. This means that the monad around a point is big enough to determine, so to speak, if we were speaking about plane geometry, the monad around a point is large enough to determine the direction of the line. This is not true in Euclid's geometry, because in Euclid the monad around a point consists just of the point itself, and surely a point cannot determine the direction of a line. Well, a corollary or consequence of this principle, that the monads around points are big enough to determine the directions of the line, is that if two lines are tangent to each other at x, then they are equal. They have the same intersection with the monad. That was the definition of tangency. So if lines are tangent to each other at a point, the two lines have to agree. So therefore, it's clear that we again, for simplicity, talk about curves in the plane. Given a point on a curve in the plane, it can have at most one tangent. Well, I should say, given a subset of the plane and the point in it, there's at most one tangent, and then I should define a curve to be a subspace where at every point there is a unique line which is tangent to it. Well, I should also prove something. It's not easy to. The synthetic method is not very good for proving things. We're so used to do it by calculus, but something can be proved. Namely, suppose that you have a curve. Then I say that it's contained in the envelope of its tangents. Well, take a point Q on the curve. Here we have the curve. Take a point Q on it. I want to prove that then Q belongs to the I think I missed a slide. So let me do it. What is suppose you have a family of subspaces parametrized by a space T. Then the characteristic point for the parameter value T, or the characteristic set for the parameter value T, is nothing but it's not a limit of something, but rather it's the intersection, or better say, the characteristic at the parameter value T0 is the intersection of all the neighboring spaces of ST0. Take all neighbors in the parameter space of T0. Take the intersection. That's the characteristic point. And the envelope, if you want to have it, then it is defined as the intersection of all parameters of the characteristic. So what replaces the limit notion is the intersection of all neighbors. The characteristic was take the limit of intersection of any two neighbors and let the parameter t approach t0. Here you take the intersection of all neighbor curves or whatever they were. Okay. I'm going to prove that the point Q on the curve belongs to the envelope. In fact, I'm going to prove that Q belongs to the characteristic point of the family of curves, which means that I should prove that for any neighbor point, well, the parameter space is here the curve itself. So I should prove that Q belongs to the intersection of all the neighboring tangents. Well, take any of these things, any Q prime neighbor to Q, which is also in K. Then since TQ prime is tangent to the curve at the point Q prime, this means by definition of tangency that K and TQ prime have the same intersection with the monad around Q prime. But Q belongs to the monad around Q prime because it was assumed to be a neighbor point of Q prime. So Q prime belongs to, since Q belongs to both K, the curve, and is a neighbor to Q prime, it belongs to the left-hand side, hence it belongs to the right-hand side, hence it belongs to TQ prime. So in this way you can do synthetic proofs about envelopes. Well, still, Euclidean geometry is nice, but the great advance, of course, came when, at the time of Descartes, I think, one invented the notion of coordinate plane, the Cartesian product of two lines, because this allows you to make coordinate calculations. Well, the fact that the line could be equipped with the structure of a commutative ring, that was essentially known already in the Greek synthetic geometry, because the addition is just concatenation of line segments, and multiplication can be deduced from the construction of fourth proportional. So the fact that the line has a ring structure, grosso modo, goes back to the Greeks. So because you have the ring structure, you can consider the subset which is the main actor in the axiomatics, namely the set of those elements on the line which have square 0. And since you now have, since the time of Descartes, have R cross R, you can display functions like the squaring function x maps to x0 in terms of its graph. For instance, you can have the graph of the function x squared, which is a parabola, of course, drawn here. And I should say that a picture like this was controversial already at the time of Euclid, because in Euclid's strict geometry, which depends on the law of excluded middle, the parabola and its tangent line, which is the x-axis, have only one point in common. The Greek sophist philosopher Protagoras had used a picture like this, well, actually with a circle and its tangent line, to ridicule Euclidean geometry, because everybody can see that there's more than one point in here, and in fact the tangent line is determined by the set of points where they agree. And from this, since you know that the tangent line is the x-axis, you can conclude that the neighbors of 0.0, in other words, the point of the graph where x is neighbor to 0, must also have x squared equals 0, must also have x squared equal to 0. So you can immediately conclude that the monad around 0 on the line is contained in D, contained in the set of elements of square 0. So now we postulate. Now we have to make, so to speak, models of the neighbor relation. The first thing to do is to say what are the neighbors of 0 on the line, and we not only want to say that the thing we already knew, namely that the monad around 0 is contained in D, we say that the monad around 0 equals D. So in other words, we're saying that a point is neighbor to 0 precisely if its square is 0. Well, since the translation maps of the line preserve the neighbor relation, it follows immediately that 2 points on the line, x and y, are neighbors if and only if their difference has square 0. And now we could define the neighbor relation on any space whatsoever by declaring it what the functional analyst would call the weak way, namely saying x and y are neighbors in the space M, precisely when for all maps alpha into the line, the 2 points are mapped into neighbor points. Well, the fact that any alpha takes neighbor points in M, to neighbor points in R, that's automatic because we're assuming all maps preserve the neighbor relation. So the interesting thing is that 2 points are neighbors. For that it's sufficient that whenever you take a function, scalar valued function on the space M, then you get neighbor points in R. And then it's absolutely trivial piece of category theory that any map preserves the neighbor relation if we define a neighbor relation in terms of in these weak terms. I should say this weak way of defining the neighbor relation is not really adequate. I should say for any locally defined function alpha, not for all functions alpha. For instance, when you come to algebraic geometry, there are many good spaces like projective spaces where there are no globally defined scalar valued functions at all. So there you have to be a little more sophisticated. But for the time being, I'll just assume this weak determination. Well, I have already put the first main action on the blackboard. Namely, any map defined on this set D, the neighbor elements of 0 on the line, any scalar valued function on D is of the form A plus D times B for unique A and B. This has to be true in parameters. That's also a piece of categorical logic, so to speak, that by a point, we don't just mean a global point, but a parameterized family of points. So also a map from D to R is really be thought of as a parametrized family of lines. In other words, the f in the action that may be parametrized by a parameter space I, and in this case the unique A and B asserted by the action are also parametrized points, parametrized by the same I. You can, if you use Cartesian closeness, which you have present in a topos at least, but then you can express it more succinctly and without explicitly talking about parameters, namely that a certain map from R cross R into R to the D is an invertible map. Well, the map from R cross R into R to the D you may describe in terms of elements, or in terms really of parametrized elements, in this way. An element in D maps to A plus D times B. An immediate consequence of the uniqueness of B here. Well, the A you have here is clearly going to be the value of f at 0, because if you put D equals 0, you have to get f of 0. So A has to be f of 0. But the unique B, which the axiom asserts, is a new thing which deserves a new name. And that's essentially the derivative of f at 0. Well, it will be, the uniqueness of B implies that you can cancel universally quantified D's, meaning that if dr equals ds for all little d in capital D, for all, then you can conclude that R equals S. Here you can again see the fact that the theory is incompatible with that part of Euclid's theory, because with Euclid, the only point on the line which has square 0 is 0 itself. But in this case, the D up here is 0, so if 0 times R equals 0 times S, you can certainly not conclude that R equals S. But on basis of the axiomatics, you can. So you may formulate this in sort of social terms, namely that these D's in capital D, they are to be considered infinitesimals, they're small. But collectively, they are strong enough to that they can be cancelled. In Euclid, it's only invertible elements that can be cancelled. Individually, an element D of square 0 can of course not be cancelled because it's nilpotent. The geometric principle that I was stating before, that two lines that are tangent to each other at a given point x are equal, is a geometric manifestation of this cancelling of universally quantified infinitesimals. Well, since the axiom is true with parameters, we can consider an arbitrary function from the line to itself and a fixed point x, and then we can consider the function d maps to f of x plus d, and then the axiom applied to that function would give that f of x plus d is for all d equal to f of x plus d times an element b, uniquely determined element b, which deserves the name b prime, f prime of x. So in this sense, you may also say that the axiom expresses that for elements of square 0 you have exact Taylor expansion, and that this characterizes f prime of x. So elementary differential calculus is available on basis of this axiom. Of course, since everything works with parameters, you may also have a parameter space M. So if you have a function from R plus M into R, and a given x, and a given x in R and a given y in M, then f of x plus d times y is of the form f of xy plus d times a unique scalar, which we denote df dx at x comma y, of course. So we have partial derivatives as a special case. How much time do I have, Mathieu? So, I'm going to present several other axioms, but they're all instances of a definite axiom scheme. So it's not really I pull an axiom whenever I need it. There's an axiom scheme parameterized by the family of Weyl algebras. A Weyl algebra is a commutative, let's see, algebra over the rational numbers, which is finite dimensional as a vector space over Q, and where the nilpotent elements form an ideal of codimension 1. The most simple, non-trivial Weyl algebra is a two-dimensional one where you associate to the rational numbers an element epsilon with the with square zero. It's called Q epsilon, and that is the one that gives the first axiom. Mathieu, how long time do I have?
10 more minutes.
10 more minutes, okay. Now, by just iterating the axiom, then you can prove that any function on d cross d is of the form a plus d1 times b1 plus d2 times b2 plus d1 times d2 times c. That's an immediate consequence. It can also be derived as an instance of the axiom scheme, namely by taking the Weyl algebra with two indeterminants, each of which have square zero. But we cannot conclude that d1 times d2 is zero, even if d1 squared is zero and d2 squared is zero. We cannot conclude that the product is zero, because that would contradict the uniqueness of C in this thing we derived on the top of the blackboard. And this is also enough to tell you why you cannot assume that the neighbor relation is transitive, because if it's easy to see that the neighbor relation is transitive, it's the same as saying that the D is stable under addition. But if the sum of two elements of square zero is also of square zero, so if D1 and D2 have square zero, and the sum also has square zero, then you expand. Since this is zero and this is zero, you conclude that this is zero, and since we are over the rational numbers, you can cancel 2, so d1 times d2 is 0. But we knew that we could not conclude that just on basis of d1 and d2, each having square 0. So we can consider a smaller object called d2, like that, which consists of those pairs of elements in R2 where the square of the first is 0, the square of the second is 0, and also the square of the product is 0. And this is a proper subobject of D cross D. So it's a proper subobject of D cross D. And axiom 2 says that every map from this smaller object to R is of the form A plus D1B plus D2B, D1B1 plus D2B2. This, of course, would also follow from the if we knew that we could extend maps from D2 into D cross D, but this we cannot do without. I should mention a few other Weyl algebras. They generalize those we have looked at. They generalize D and the D2, namely DKN, that consists of n tuples of elements such that the n tuples of numbers such that the product of any k plus one of them is 0. And that's a representer of k-jets in Ehresmann theory. And the axiom corresponding to that Weyl algebra that defines that set is that every function on dkn to R extends uniquely to a polynomial function of degree less than or equal to k, which is the kth order Taylor polynomial. But there are other interesting Weyl algebras. One of them is relevant in when you have a Riemannian metric available. Namely, it's one that allows you to describe the Laplace operator without having to first define the second order partial derivatives. It's the Weyl algebra which defines an object in R2 given by x1 squared equals x2 squared and x1 times x2 is 0. I shall not go into that. But let me return to envelopes. That's really a triviality now from the action that the characteristic, which in our perspective is prior to the envelope, that the characteristic of a family of subspaces, say a family of lines in space, can be described as the intersection of all the neighbor lines. That this is correct. Well, to make the comparison, we have to do as they do in calculus books. Say, how can we describe a family of surfaces? That we can only do by having a function. Well, now I'm talking about surfaces in free space. That I can only do if I have an analytic representation, a function in 4 variables, such that that the subspace corresponding to a given parameter value is a 0 set of. Then to say that a point x, y, z is in the neighbor surface is to say that f, x, y, z, t0 plus d for any d in capital D is 0, but by Taylor expansion this means that this is 0 and that can only be 0 if both this and this is 0, and these two equations are what defines in the analytic treatment the characteristic curve in this case. But note that the description I gave in terms of intersection of families doesn't depend on having the surfaces ST individually parameterized. Well, I think I'm going to skip this. I was going to give a condition for when a distribution, a geometric distribution in the sense described before, is involutive in case the distribution is given in terms of a differential one form. But I will skip that and go to some historical remarks. Namely, the quest for a theory of neighbors is old in differential geometry. I prefer to say neighbors rather than infinitesimals. I argued already that. And for this, I would like to read a quotation from one of Sophus Lee's fundamental texts on differential equations, which he, following Monge's geometric theory of differential equations, that was some of Lee's first basic works that led to much of his other works. He says that, let me rather, you have probably read it already while I've been talking. Otherwise, let me take the punchline. He says, as expedient as the synthetic method is for discovery, as difficult it is to give a clear exposition on synthetic investigations. And in some sense, one may say that the present form of synthetic differential geometry improves the situation somewhat. And one guideline for this improvement, which led to the axiomatic or synthetic form of differential geometry, came, as I have mentioned already, with the consideration in algebraic geometry of what they call the first neighborhood of the diagonal of a scheme. I shall only discuss affine schemes, meaning schemes described by commutative, say, Q algebras. M is the multiplication map of a commutative algebra A, and it has a kernel I. Since M is a ring homomorphism, the kernel is an ideal. You may form the square of that ideal. Since that is smaller than the ideal itself, you quotient out something bigger and get a surjective ring map here in the category of affine schemes, which is just the dual of the category of commutative rings. The same sequence you have here gives rise to to scheme maps. A tensor A represents M cross M. A tensor A modulo the multiplication ideal represents M, or better the diagonal of M inside M cross M. And M1 sits in between. It's represented by that ring. That was an invention of French algebraic geometry about 50, 60, 70 years ago. In this perspective, the line that we have been trying to axiomatize is just the affine scheme corresponding to the free Q algebra in one generator, the polynomial algebra in one generator, and D is the one that corresponds to the ring of dual numbers, which is Qx modulo the ideal x squared. And the relationship between the two aspects in this perspective is that the first neighborhood of the diagonal of R is isomorphic to R cross D. Here's R cross R goes up like this. The first neighborhood of the diagonal goes like that, but the fiber over an individual X is isomorphic to D, which is that little piece here. And this not only works in algebraic geometry, there's been some efforts and some books even to import it into differential geometry. I can mention, for instance, the book by Poincaré and Spencer called Lie equations, where they also talk about prolongation spaces, but in the for differential geometry, i.e. smooth manifolds and things like that. I should also mention Kähler differentials. See, in this was the ring that represented the first diagonal of the affine scheme given by the ring given by the ring A, and the ring corresponding to an affine scheme you think of as the ring of scalar valued functions on that scheme. So this ring is the ring of scalar valued functions on the diagonal of the affine scheme given by M, and this submodule of it, I modulo I squared, is therefore the set of scalar valued functions on this first neighborhood of the diagonal, which vanish on the diagonal itself. And this is exactly how Kähler defined the notion of scalar-valued differential one form, the Kähler differentials. So in that sense, the combinatorial definition of differential one forms goes back to Kähler, at least for scalar-valued forms. The modern form of SDG, which I have been expounding here, as I say, is a synthetic theory where you don't assume that the things you're talking about are affine schemes or anything special. You're talking axiomatically about a category with a ring object, commutative ring object, and describe D as the set of elements of square zero. It's a tangent bundle representer. And therefore you would like R to the D, i.e. the tangent bundle of R to be R cross R, which is one formulation of the axiom 1 I was presenting. I should say that much of the theory here is you can find in the last book mentioned on there, which quite recent Cambridge publication, Synthetic Geometry of Manifolds, which concentrates on the neighbor relation. Okay, I should make some comparison with non-standard analysis. In non-standard analysis, you also have a neighbor relation, but there it's essential that it is transitive, whereas in synthetic differential geometry, it cannot be transitive. Also, non-standard analysis is not an axiomatic theory, but a descriptive one. It depends and describes properties of the real number system, because one of the fundamental things in non-standard analysis is that every finite non-standard real has a unique standard part, which is an aspect of the completeness of the real number system. You can also have an axiomatic theory of starting with a topos, say. I did some investigations together with Chris Mikkelsen in 1972, and Nelson has some based on axiomatic set theory in 1977. I'm finishing in 2 slides, I think. When you have synthetic theory, you would like to know some models for it. But I would like to emphasize that models are not essential. Euclidean geometry has been very useful for a couple of millennia before what in modern times would be called a model of Euclidean geometry was ever invented. Because when, for instance, was the real number system invented? Of course, we get the inspiration, and also well, I'm not going to advocate why one should have models. Of course, we would like to have models. Models come in 2 main species of the models we know. The algebraic models I have already sketched how they come from the theory of affine schemes. Well, affine schemes is not a topos. You can make presheaves on affine schemes, then you have a topos. And since presheaves are contravariant functors from affine schemes, this is the same as the covariant functors from commutative rings or commutative Q algebras. They were just so this basic algebraic model just consists in covariant functors from the category of commutative Q algebras to sets, and R, the ring, the basic ring, is in this aspect just the forgetful functor from rings to sets. There are subtopos of this presheaf topos, which, for instance, will allow you to force the ring object to be a local ring object. all this is discussed quite extensively in the book by Mathieu and Gabriel. Then the analytic models, they depend on importing the wisdom from algebraic geometry by, instead of considering commutative Q algebras, to consider to consider the algebraic theory whose n-area operations are all smooth functions from Rn, real numbers, real n-dimensional coordinate vector space over the real numbers into R. Smooth functions, simply. They're the main technical tool for building what is called well-adapted models. A well-adapted model is a topos with a full and faithful function from the category of smooth manifolds into that topos. They should preserve transversal pullbacks, in particular products. So the well-known ring of real numbers goes to a ring object inside the topos. It should preserve coverings. I already mentioned that. The third condition that we axiomatically, or the ring inside the topos, is to be the image of the ring of real numbers. It should not preserve pullbacks which are not transversal, because if you, for instance, take this picture again, the parabola and the x-axis inside the plane, if you take their pullback in the category of manifolds, this is just a point, namely this point here. But you know that inside the model, it's going to be bigger. So it's clear that we do not want this pullback that defines that point in the category of manifolds to be preserved. Rather, in the well-adapted model, you get a bigger object, which is not a manifold, namely D. And such models exist. And as I say, here's the algebraic theory that allows you to construct algebraic models by, so to speak, copying the wisdom of algebraic geometry. So, that's all.
Is there any question?
Obviously, you have to work in a category which looks very much like the topos. The formulae you have still on the blackboard involve arbitrary unions and intersections, so that cannot be done. And you have also a formula involving exponential, so that justifies the use of those. However, in your, what you call chapter 1, you gave very general definitions, and maybe 30 of them, like characteristic, envelopes, etc., etc. There's no axiom, and as far as I can see, you can prove nothing. You didn't prove there was only one proposition which is trivial can be.
Mm-hmm.
So that's the point of so many definitions without any result. That's my question.
You want me to? Well, the point is more to give the language, as Sophus Lee expresses, by which these synthetic considerations can be communicated. And for instance, I can communicate, for instance, the notion of affine connection in very simple terms for people who do not know multilinear algebra, say. There are many proofs that you can do in this, but I have been asked not to present much. I'm just saying that even...
There are proofs?
No. As I said, the synthetic method is something from which you get insight, and which most proofs, and also if you go into my book, a main point is that you make the definitions and notions in a coordinate-free and preferably synthetic way. All proofs you resort to coordinate calculations. Not much. As Jean Benabou pointed out, there's in chapter 1 there's only one trivial proof, but there are several non-trivial notions. If you want to prove things about them, coordinatize, but make the notions before you coordinatize.
Yeah, question? You say that probably models are not so important to take advantage of this approach, but when you have the correspondence between space which satisfy the axiomatic of SDG with the space which are the usual smooth space or the usual Euclidean space, subspace, and so if you have this correspondence, of course, I suppose that investigating models, there are also models which doesn't fit in this correspondence. So, do you think there are some space which satisfy SDG and which have no correspondence with the old objects so that maybe the insight you gain by using all this axiomatic gives something new and interesting?
Well, as I was trying to explain at the end, the models come in two varieties, the algebraic and the analytic, those that depend on the real number system. And this axiomatic theory comprises both. So you may say the fact that in algebraic geometry you can talk about tangent bundles and so on. Why is it that, what relationship does that have to tangent bundles of differential, usual differential analytic geometry? And this connection is pointed out by this axiomatic theory, and there's certainly things in algebraic geometry that doesn't hold in the smooth world.
Any other question?
Why do you think synthetic differential geometry is not more widely used? Do you think it has some drawbacks that prevent it to be useful for concrete algebraic geometers, or is it just historical reasons, or is there some obstruction? Or what is your opinion on that?
That's a very good question. I don't understand why. I don't understand why it's not a more common tool. It has been called for ever since, well, for instance, by Sophus Lee.
Any more questions? Comments, remarks?